Hello and welcome to Easy Projects. So today it's going to be something very exciting. Look what was in the mail today. It's the Batterisers. It's been quite a long time since they launched the campaign, so I was starting to think they would never ship them, but it turned up finally, so now we can have a look at them and test them. To those of you who haven't heard about Batteriser, or Batteroo as they're called now, it's basically a little sleeve like this that you can slip over your used batteries, and it would extend the life of the battery by 8 times, as per their original claim. They have revised that a little bit since, but they still claim that you can get a lot more energy out of your batteries when you throw them out. So the product has been debunked a lot of times before it was even developed by people like EEV Block, and they came up with a pretty good conclusion of why this would be a fail, basically. So you can go and watch their videos, it's great fun. The most funny thing is that Batteroo, the company, kinda declared war on those guys, and they used all kinds of cheap tricks to try and get the videos banned, and they said that they were just amateurs that knew nothing about batteries, because apparently batteries are something very special. Who knew? But now we're finally done with all the conspiracies and we can actually do a physical test of the product, because sure it works now that they delivered it. Doesn't it? Let's find out. So it came in this pretty anonymous box, except it says Batteroo on the side, so yeah, guessed what it was. Then you open it and you get the regular marketing stuff on the inside. Thank you. By supporting our crowdfunding campaign, you and thousands of other forward-thinking individuals from around the world have brought Batteroo to life. Thanks to your help, we can now tap into the energy that's usually thrown away and reduce the amount of disposed batteries in landfills. On behalf of our entire team, welcome to the Batteroo community. Yeah. Thank you very much. And inside the box we had 2 of these carry cases, I think it is, each containing 4 of the Batterisers, and shows how to use them, and there's a little warranty and disclaimer that you shouldn't use them if they're bent or scraped, or yeah. Then you get the carry case here, and I must say it's made really nice. It has a little hinge here. It's a real lock, and it's fairly sturdy. It wouldn't open itself, and you gotta say that the actual product looks very nice. It's not, they didn't cheap out on making these. It's like it looks like it's been laser cut, the Batteriser text into the sleeve here, and it looks like it's been press formed, and then the PCB is glued in place in the top here. So just looking at the design, I kinda like it. It's well made. So if you look at the document they included here, you can boost the batteries in 3 different ways. You can extend the battery life of your device. You can maximize your device's performance. And you can bring perceived dead or zombie batteries back to life. So they tell you that there's 2 different kinds of products. There's a passive product, like an old school flashlight with a light bulb in it. It will keep on working until the battery is completely dead. Hence, you would think, why would you need a Batteriser? In my opinion, that's probably the best use for it, because it will dim over time and you will just get pretty much unusable light in the end. If you wake in the Batterisers, it will keep on working at full brightness until it just suddenly dies. So I guess that's what they mean with maximize the performance of the devices. And then we have the active devices, which has electronics in it. It will have a minimum operating voltage, and once it drops below that voltage, it will just stop working instantly. So that could be something like a camera, or a Game Boy, a multimeter, calculator, something like that. But anyway, let's get on with the testing. So first of all, let's just test if they work at all. So let's focus in the flashlight here. It's one of the old Mac lights, which has a light bulb in it, and it uses 2 AA batteries. So if I shine that over here, and I use a fixed exposure, so any difference in light output should show up on the camera. So this is without the Batteriser, and here is with the Batteriser. And I can see that it's clearly brighter than it was before, so it does indeed boost the voltage and give the flashlight the 3 volts that it actually needs. And the Batterisers just like barely fit in the flashlight here. You can hear it actually scrapes against the inside of the flashlight, but they do fit. Just. But you have to like wag it against your hand to get them out. So if we measure the open circuit voltage of the battery here, you can see that it's 1.4 volts. But it won't be that when it's in the product, then it will drop lower. But if we use the Batteriser sleeve, let me see if I can hit the contacts here. We're at, oh, that's strange. It's definitely 1.5 volts, but it looks like it's jumping up and down. Maybe I need more pressure on the contacts. No, it does seem to be a little bit all over the shop. That's interesting. So let's just check it with the fluke. It's a little bit faster. And sure enough, it is jumping up and down. There might be a logical explanation for this, because this is basically open circuit, so we are not drawing any current except the 10 mega ohms input impedance of the multimeter. And to keep their device from not using any power, it might shut down and just measure the voltage on the terminal here and then turn back on once that drops below a certain threshold. So they're basically turning on and off the converter to save power. That might be the explanation, but then it should go away when we put a load on it. So a typical load might be 3 milliamps, and I got a 470 ohm resistor here. And when I connect this to the battery, we will draw around 3 milliamps. So let's try and do that. So I'll just connect the banana clips to the multimeter probes. And here you can see with the 470 ohm load, we get a nice stable DC voltage of as close to 1.5 volts as you want to be. I think there's one slight problem here if you really want to maximize the performance, because when you get a new AA battery straight out of the pack, it won't have 1.5 volts, more like 1.62 or something. Let me get a new one. So let's get a new one out of the pack, and let's measure it here. It's still with the resistor, and you can see it's 1.61 volts. If I can keep the probes on here. So that's with the load, and if we remove the load, it's probably closer to 1.62. No, it isn't. 1.61. But that is, of course, only when it's new. It will drop down to about 0.9 volts before it's completely dead. And the nominal voltage, so I guess the average voltage, you could say, is 1.5 volts. So it's fine that they put it at 1.5. I can't really complain about that. It is the nominal voltage. But it will mean that your device will have more power when you use new batteries still. So I wonder what happens if we put a fresh battery with 1.6 volts into the Batteriser. Will it just pass that straight through, or will it regulate it down to 1.5? so it passes it straight through. And I guess that's what you want. You don't really want to regulate it down, of course. So there's a few things I want to test, and the first one is how much power does the chip inside the Batteriser actually use when it's just connected onto the battery, because there's devices that use very little power but still require a certain voltage to operate. One example could be some of the cheap digital clocks like this that are radio controlled, which means they can pick up the time from a radio signal. When the battery gets too low, it won't pick up accurate time anymore, and it might not switch over doing daylight saving time and stuff like that. So you would have to change the battery just to get it to update the time. But there is clearly still enough power in the battery to operate the clock. It's just that the radio receiver probably doesn't get enough power to get any signal. So if the Batteriser really doesn't use any significant current, then it might be a good idea to put a Batteriser in the clock with the battery to keep the voltage at 1.5, and it will be able to pick up the radio signal. So the thing is, the clock uses very, very little power, and a battery can last for years. So if the Batteriser uses any significant current compared to the clock, then you might as well just change the battery, because it will run out anyway. So let's test that. And to do that, I'll be soldering 2 wires onto the positive terminal in here, and we might solder a wire to the negative as well. Yeah, we don't really need the 2 wires right now, but we might need them later. So I soldered it on there, and I tried to be very careful not to melt any of the potting compound that I used to encapsulate the components. So I'm taking a battery holder here. It's designed for 2 AA batteries, but I just soldered a wire to the spring here so that we can just use one cell. And I'm going to solder the negative to the negative terminal of the Batteriser, and then we can connect the positives together as well, forming the same circuit as if the battery were in the Batteriser. So I thought this was steel, but it might very well be aluminium, because the solder just doesn't stick at all. Nope, that's not going to happen. So it might be that it's actually anodized aluminium and not coated steel, which I thought to begin with. So I'll go and wash off the flux residue here, and we'll just use a clip. So it's ready here. We got the negative connected together, just as if the battery were in the Batteriser, and we have wires on the positive terminal here, and we have the positive wire from the battery here. So now we can measure the current going inside the Batteriser itself before we see any voltage on the output. So I just moved the multimeter to the bench here, so it's a little bit easier to see what's going on. And we are measuring microamps. I don't expect it to be more than that. So let's see. Oh, that's interesting. Let's just select the manual range. So it looks like it occasionally goes up to 32 microamps. So let's do a min-max average on that. And letting it run for a little bit, we get around 16 microamps. So when you have a varying load like this, it can sometimes be useful to look at the histogram of the multimeter. So you can see most of the samples are within this block here, but we have a fair amount a bit lower, and some are a bit higher as well. The average is still 16 microamps, and we have a standard deviation of about 9 microamps. So one thing is looking at the numbers on the multimeter to get the current consumption. But if you want to know what the actual waveform looks like, we can use the EEV block microcurrent. It will take a current input, and it will convert that to a voltage, which we can measure on the outputs here. So we'll start by using the milliamp range, and I just use a very short ground clip on the multimeter here just to lower any ringing that we might get from sharp edges. We'll probably still get some ringing and some noise, but at least we can try to do it as good as possible. And now we can see some pulses on the screen there, but if we put it into the normal trigger mode, it will trigger just on the pulses. Now to get an idea of the current consumption, we can just count how many squares are under the curve here, or we could use an integral function. But let's just do a rough estimate here. If we take this piece and put it up here, we have like 6 squares there, 7, 8, 9, probably 10, right? So we could convert that into one pulse, 10 squares high of current, right? Instead of this, we just say it's like that instead. So that would give us 200 milliamps over 10 microseconds. So the second thing is we need to know how often this pulse repeats to calculate the average current. So put it on normal trigger mode again. We will zoom out until we see it, and there we are. So 175 milliseconds between the pulses, let's just call it that, and we need to take the inverse of that to get the frequency. And that's basically what we saw with the voltage in the beginning going up and down. So it looks like they used the pulse frequency modulation when we're drawing very, very little current. So if we inverse that, we get 5.71 Hertz. And if we then multiply that by the amp seconds used in the pulse, we get an average current of 11.4 microamps. But here we're not taking into consideration the tiny amount of current being drawn all the time, even when there's no pulse. I don't know if we'll be able to measure it, but we can give it a try at least. So I'll put the microcurrent into the microamp range. So we are saturating the output, as you can see here. I don't think it's an entirely good idea, but let's see if we can see what the current draw is before the pulse here. Let's perhaps do a few averages on this to get the average value. Oops. So using 16 averages, we get around 3 microamps of current before the pulse. I can't really do it any more accurate than this, but let's just try and unplug the Batteriser and see if it goes to 0. We need to go to auto. Yes, and we are averaging around 0 microamps without anything connected, so I think we can accept that. So if our measurements were accurate, we get 14.42 microamps of average current being drawn, which is pretty close to what we got on the multimeter. Let's just plug it back in. And on the multimeter, again, it's climbing up to around 16 here. So that value is fine, but what does it actually mean in the real world? Well, that a typical good AA alkaline cell will have 2700 milliamp hours or 2.7 amp hours. If we divide that by our 14.41 microamps, we'll get how many hours this will last. And that's 187,369.9. So basically 70. So if we divide it by 24, we get 7,807 days. And if we divide that by 365, we get 21.4 years. Which basically means that the battery will be dead before the batterizer has used all the capacity. So at least this is pretty good. Let's just for comparison measure the current consumption of a typical watch like this. And to do this I just removed the battery and hooked on the alligator clips to a battery with the multimeter in series. And you can see the clock is now powered up. If we look at the multimeter, you can see it's using an average of about 50 microamps. It goes up to 60 some. But let's just get the average. So it's around 56 microamps for a watch. This particular one is not radio controlled though. So let's see how that changes when we take the battery, put it into the batterizer, and put it into the watch. I still do it on the bench here, and with these low current values it shouldn't really matter with the cables, but I am using alligator clips to connect to the watch. So I have the battery here, which connects to the batterizer, and I'm measuring the current between the battery and the batterizer with the multimeter, and then I connect to the outside of the batterizer, and I connect that to the watch here. So without the watch connected, we get our 16 microamps. So let's try and connect up the watch and restart the average. So let's try that again. It went over range on the multimeter. So let me connect it and restart. And let's just let it run for a couple of minutes. So it's been a bit more than a few minutes, but at least we get a pretty accurate figure now of 77.7 or 8 microamps. So the current without the batterizer was 55 microamps, and now with the batterizer we have 77.9 now. So if we just say that's 22 microamps more than without the batterizer, and we know that the batterizer itself takes at least 16. So we're only losing about 6 microamps in the conversion losses, which is pretty damn good actually. So with the batterizer in this watch you still get a runtime of about 4 years, compared to 5.6 years without the batterizer. But keep in mind that you will probably change the battery in the watch before that, because it gets very dim. And let me just find another watch which is radio controlled, where that watch simply won't sync up with the radio signal if the voltage gets below a certain threshold. I don't really know the actual value, but at least once a year you need to change the battery. So I just went and grabbed the watch that I was talking about here, and as you can see this actually uses 2 batteries. So it's a 3-volt watch, and it also uses a bit more current, around 245 microamps. Or let's just call it 243. With that amount of current it should last 1.27 years, but it already has problems receiving the radio signal after half a year. But if you kinda take it outside then it will do it, but after 1 year there's no chance. So let's see if I can use some fairly dead batteries and get it to get the radio signal with the batterizers. So I just measured these batteries, and they measure 1.41 volt. And let me tell you, it's a pain in the ass to put these batteries in when they have the batterizers on, because the terminal on the batterizer is just these 4 pins here, and when you try and push it in, it will kind of grab this pin when you try to push it down, and it will, I'm pretty sure you'll break this if you're not careful. So you kind of have to, like, you really have to push hard against it and make sure that it doesn't rub against the contact. So actually here you can see what I mean with the tabs. Now when I press it down, one of those little tabs on the batterizer get caught on the tab in the watch, and if I just press it down it will like bend out and flip over. If you do that a couple of times it will just break off. And also the batteries are very, very tight fit in here. They can just barely fit with the batterizers on top. So I'm out here in the garage to test if the clock will actually sync up with the dead batteries when we put the batterizers in. It doesn't look promising because you can see it only has 1 bar of signal, whereas if you put like fresh batteries with 1.6 volt on them, if you put those in, it has full bars. Again, it is a crap watch, but this is one situation where the 1.5 volts being delivered by the batterizer might just not be enough. Unfortunately, it doesn't look good for the batterizers here because 20 minutes has now passed and it still didn't sync to the radio signal. In fact, the REC light has even stopped flashing. So let me just try with some fresh batteries so that we know the watch is indeed working. So let's turn on the watch again. Now using fresh batteries straight out of the pack. So we now have 3.2 some volts at the terminals, and you can see the receive signal is up to full. And now we just wait and see how long it takes to synchronize. And after about 5 minutes it picked up the signal and we can see the time. And yeah, it's getting pretty late. I don't know exactly when it did. I just went to the bathroom and when I came back it already picked it up. So just less than 5 minutes. So this is not really a problem with the batterizer, as I mentioned earlier. 1.5 volts is the nominal voltage of a battery. It just happens that this watch here doesn't work at 1.5 volts or 3 volts because we have 2 batteries. So it's a poorly designed watch, which then in turn means that we can't even fix it using the batterizer because the voltage is too low. Basically some of their false claims was that a lot of products drops out at 1.3 volts, 1.35 volts or thereabout, and then they fix it by boosting it up to 1.5, and then you can use like the last 80% of the battery, which, you know, it's bullshit. But in this case, one particular product, it drops out at above 1.5 volts. It doesn't drop out, it still works, but it doesn't update the time. And even using the batterizer still doesn't work. But it was worth a shot anyway. If the watch had worked at 1.5 but didn't work at say 1.4 volts, then it would be beneficial to use the batterizer because you could get more life out of your batteries. But yeah, in this case, not so much.